Hi all, and thanks for joining this webinar. My name is Rohan and I am from Speedgoat. Welcome to this webinar where I will present how you can innovate and teach real-time control designs with special focus on your needs as a researcher, professor, or a student. MATLAB and Simulink are used at universities worldwide. Key applications certainly are design and exploration of novel control concepts and to teach controls theory. We will show you in today's webinar how Speedgoat hardware combined with the MATLAB and Simulink environment from MathWorks helps in expediting your projects in real-time controls design and testing. We will show you how you can easily connect the Speedgoat hardware from the MATLAB and Simulink environment, apply our ready-to-use reference application, and get up to speed with the tools used to design and test controls design algorithm. But before we begin, let us look at some of the key focus areas for academia in the field of controller design and testing. You probably focus on research and publishing, or you are teaching controls, both theory and applied knowledge, in a way that makes your students ready for the industry of further research. Or you want to take part in student projects and competitions and win them and be at the forefront of innovation with state-of-the-art technology. Or you are a future entrepreneur and want to evolve your academic project or research to a startup. In today's webinar, I hope you will find yourself in one or more of these areas. We will keep coming back to this slide as we go through real-life examples of how researchers, professors, and students worldwide use the Speedgoat plus MathWorks solution in their area of work. Let's start with the research focus by looking at the work done by a research institute in Strasbourg, France, the INSA Strasbourg, which specializes in applied research for engineering students. They have worked on an innovative way to use variable reluctance synchronous motors as an alternative to permanent magnet synchronous motors. Let us first look at the context of the problem. This is the model of a battery electric vehicle. These vehicles use large traction battery pack to power the electric motor. Most of the electric vehicle manufacturers use the permanent magnet synchronous motors, or PMSM in short, in their electric powertrains. This magnet motor is composed of rare earths whose price is constantly increasing. Faced with this problem, INSA Strasbourg is involved in the European Research Project Vehicle, which is funded by the European Union through the Interreg 5 program and supported by Offensive Science. This project proposes to use variable reluctance synchronous motors as an alternative to PMSM motors. This motor is free from rare earth metals and has a better efficiency compared to other magnet motors. This magnet-free and robust motor, however, suffers from two major drawbacks, which are relatively high torque ripple and significant acoustic noise. To overcome these disadvantages, the research team at INSA proposed the use of advanced control algorithms to present this motor as an alternative to other magnet motors. Let us look at how did they go about designing the control algorithms. In general, the controller algorithms are handwritten code that are deployed onto an electronic control unit which is connected via I/O channels to the electric powertrain or the system under test. This is dependent on the architecture of the controller, which can be an MCU4 or an MCU7 or any other controller where you need to write long software code, and this can be riddled with bugs. Also, this can be quite time-consuming. To circumvent this problem, the researchers at INSA used the Speedgoat Performance real-time target machine as a prototype of the controller. The controller model was written in MATLAB and Simulink and was deployed onto the real-time target machine, which is then connected via analog and digital I/O to the system under test. This way, the Speedgoat target machine acted as a prototype of the controller. The synchronous reluctance motor test bench looked like this, with the performance target machine as the controller connected to the synchronous motor. You can see here the target machine is connected to the workstation where you have the Simulink model developed. This model is then deployed onto the target machine. The response of the motor is checked in MATLAB. Here, you can see the motor spinning with increasing velocity. The graph shows the reference velocity to be similar in value to the measured velocity, showing our control prototyping to be successful. The motor then spins to a constant velocity and then decreases. This research shows the advantage of having a powerful controller prototyping platform to implement advanced controller algorithms. Let us look at what we saw from a typical plant controller perspective. A typical plant controller system consists of an input signal which is applied to the controller, which controls the signal fed to the plant, and in a closed loop system is connected to the output. Let's say you want to design the controller which controls the plant. This could be an ECU for a car, a FADEC for an aircraft, a PLC for your electric power system, a motor controller for your electric motor, or just about any other controller used in your industry. To start with prototyping your controller, you could use the Speedgoat hardware, the real-time target machine, as a prototype of your controller. As a next step, if you want to test your controller operation in real-world scenarios, you can do this by connecting a real controller to the Speedgoat hardware, which acts as a digital twin of the plant. As you can see, the real-time target machine forms an essential component to prototype a controller or create a digital twin of the plant. Having these customized according to the needs of your project is of utmost importance. For this, Speedgoat offers a wide range of real-time target machines. Benefit from a high power and flexibility with the performance machine. It ships with the latest Intel CPU and allows up to 50 I/O modules. The chassis is tailored for desktop as well as lab use. Depending upon your compute tasks and the number of both sensors and actuators, the performance machines are designed also for rack mounting. The mobile, baseline, and unit machines are ruggedized, hence allowing being used in prototypes or moving vehicles of any kind. Yet, they are powerful and allow for modular I/O expansion. The mobile is a compute powerhouse leveraging Intel's latest mobile CPUs, and it can host up to 14 I/O modules. The baseline is an excellent trade-off between compact form factor, power, and flexibility. It is ideal for applications requiring a small set of diverse I/O. Over 100 I/O modules are available and up to 7 can be installed. Unit machines are great for controller prototyping of size and weight constrained projects such as robots and devices for interaction with humans. So then, how do we connect these to the MathWorks MATLAB and Simulink environment? To do this, this is how a typical setup looks like. On the development computer, you use MATLAB and Simulink to create and develop a model of a complete plant controller system. For this, let's see what MathWorks has to offer for the academia. In the form of campus-wide licenses, MATLAB and Simulink are available to many universities worldwide. Used by professors, researchers, and students alike, it is available on different platforms. With MATLAB, you benefit from a programming and numeric computing platform to analyze data, develop algorithms, and create models. With Simulink, which is a block diagram environment used to design systems with models, you can simulate before moving to hardware and deploy the models without writing code. Simulink Real-Time allows you to go a step further by deploying your Simulink models onto real-time hardware, and this is where Speedgoat comes in. With this real-time hardware, you also benefit from close collaboration between Speedgoat and MathWorks. So, when you connect the Speedgoat hardware to the development computer, with the help of one click, it is easy to deploy the model onto the Speedgoat real-time hardware. To do this, however, it is essential to have seamless connectivity between the development computer and the real-time hardware. To begin with, connect via the Ethernet cable from the development computer to the host link of the real-time target machine. Open the Simulink Real-Time Explorer from the editor window of MATLAB and connect to the target machine with just one click by using the parameters as shown. After you have connected the Speedgoat target machine to the development computer, Simulink Real-Time Workflow lets you build real-time applications from the model and deploy to Speedgoat real-time target machines with just one click on Run on Target. Let us look more into what constitutes a real-time target machine. The target machine has multi-core CPU where the real-time application created from your Simulink model runs on it together with the Simulink real-time operating system. The I/O connectivity options can be analog and digital lines, communication protocols for your area of research, or other I/O connectivity options, more of which you can find on the Speedgoat webpage, and they can be used to connect to your external device under test. Automatic C and VHDL code generation allow you to deploy parts of the model either to the multi-core CPU or to one of the FPGA modules installed inside the target machine to achieve faster and more deterministic execution of your algorithms and faster communication to whatever external equipment is connected. This means you could benefit from a customized solution with the option of having higher processing power with the FPGA module installed into the target machine, meaning you could customize your target machine to be without the FPGA module or have it. So then, when do we need the FPGA module? This is based on the level of configurability and sampling rates. Speedgoat provides different types of I/O modules supporting your project. For sampling rates below 4 kHz, Speedgoat provides fixed functionality I/O modules, which are analog digital I/O lines or communication protocols for your area of research. For sampling rates above 4 kHz and up to 20 kHz, you can leverage the configurable I/O modules. These allow you to use high-frequency I/O and lots of protocols. You can configure these modules on the fly and directly from Simulink. For sampling rates about 20 kHz, you can use the programmable FPGA I/O modules. The programmable FPGA I/O modules allow you to outsource both parts of your algorithm and signal I/O to the FPGA using the HDL coder workflow from within Simulink. For more information on this, watch our short workflow introduction to FPGA technology. Let's look at further example on how the programmable FPGA I/O module was used in a real-life example by going back to the focus areas for academia. As said before, you probably want to teach controls theory to students. A typical lecture at the university consists of a theory-based lecture along with exercises accompanying them. These are filled with academic examples with generally few or none of the real-life engineering problems being discussed. This poses a challenge to train students adequately for the industry or future research in the field of controls design. But what if you could overcome this challenge if you had a ready-to-use application with hardware? Let's hear from Hans-Jörg Strude, an associate lecturer at the Corporate State University, DHBW, in Stuttgart, Germany, who used the workflow from Speedgoat with the FPGA modules to teach controls design to his students.
Hello, my name is Hans-Jörg Strude. Let me first introduce myself. I'm an expert for rapid control prototyping, working at Mercedes-Benz in Stuttgart, Germany. During the last 20 years, I gained a broad knowledge in digital system design using various microcontrollers and FPGAs. Since about 5 years, Speedgoat hardware and MATLAB Simulink are part of my everyday work. Additionally, I am working at a corporate state university in Stuttgart as an associate lecturer. At the university, I'm teaching digital system design at an introductory level. It is a mixture of theoretical fundamentals and hands-on lessons. One goal of the hands-on training is that students can leverage the power of Simulink real-time, from beginner examples all the way to more complex projects. Let me explain this project a little more detailed. The picture on the right shows the composition of the hands-on experiment. On the test board, we have two little DC motors. The driving motor on the left is directly connected to a second motor, which is used to generate load torque. To control the driving motor, three major functionalities need to be implemented. These are the control signal generation and the speed detection, which should be implemented as FPGA hardware, and the PID control of the motor speed, which is typically CPU software. Using Simulink real-time for this project offers some advantages. The ability to design and simulate the CPU software and the FPGA hardware together in a single model was of great value. In addition, the workflow to generate an application running on Speedgoat hardware was made easy. To summarize, I'd like to say that Simulink real-time and Speedgoat hardware is a perfect combination for my introductory course. It helped me a lot to share my knowledge and to introduce state-of-the-art model-based design of digital systems. Thank you for your attention.
Thank you, Hans, for showing how a ready-to-use workflow helped you teach the students a theoretical course with a practical component with cutting-edge technology. This has enabled the students to be ready for the industry and further research. With this, let's circle back again to the focus areas. You might be interested in getting your student project be at the forefront of innovation. This is the platform for you to demonstrate your capabilities to work on real-life problems and make a difference. It is essential for you to be working with state-of-the-art technology to achieve this. Let us look at how students at the Flugwissenschaftliche Vereinigung at Aachen, Germany, a flight science association since the 1920s, developed a hybrid electric aircraft to solve the problem we face today with ever-growing greenhouse gas emissions. Today's commercial aircrafts run on gasoline. As we move towards a greener economy to combat global warming, we tend to focus on electrification of aircrafts. The current state of battery technology, however, restricts a fully electric aircraft to over short-haul distances. A hybrid electric aircraft is where you can exploit the advantages of having electric propulsion along with traditional jet fuel propulsion. One such research group looking to build a hybrid electric aircraft is the Flugwissenschaftliche Vereinigung Aachen, an organization dedicated to the research and development of aircraft components and complete aircrafts for over 100 years. The latest innovation is the FAA-30, their hybrid electric aircraft, which has motors mounted at the end of the V-tail which help propel the aircraft forward. Here, you see the video of the baseline target machine prototyped as a controller of the hybrid electric aircraft. The greatest challenge they faced was with regards to building, testing, and certifying the aircraft. To do this, they needed an iron bird to test individual components, complete control strategies, and show compliance with the respective aviation authority requirements. To tackle these challenges in an efficient manner, all control algorithms were designed in Simulink. The baseline target machine was leveraged as a controller and was the heart of the iron bird. This way, the controller algorithms modeled in Simulink could be deployed onto the target machine, making the target machine a prototype of the controller that could be put on the aircraft for it to control the aircraft's powertrain. On the test bench, the target machine is controlling the motors through the I/O connectivity to connect to other components on the aircraft. This connectivity was used to perform many control tasks, to read commands such as throttle, elevator configuration, and motor control related functions from an external test person acting as the pilot. Here, you can see the test bench with the Speedgoat target machine connected to an off-the-shelf battery management system. Complex Simulink-based control algorithms are then computing torque values in real time, driving inverters, and sending commands to the battery management system over CAN interface. The battery management system observes the state of charge and battery's temperature, for example, to ensure that the batteries are in a safe state before, during, and after the flight. To do this, the team used the Real-Time Explorer to keep track of the system state. This information is regularly sent to the main controller, which can provide the pilot with the necessary information and warnings. This was done using a graphical user interface. The system was modeled using Simulink real-time, which enabled them to build a model of the system within a very short time. This shows how your research project could benefit with the Speedgoat test system. With this, let's circle once again back to the focus areas. Getting your project from the academic research or project stage to evolve into a prototype or product designed for the industry is an arduous task. There is a need for technological support to develop the product further and differentiate it according to the needs of the market, especially the ones looking to commercialize the research output from academia. We help you expedite this process to move from research in academia to a startup. You not only benefit from the Speedgoat hardware plus MathWorks environment, but also gain with access to the technical support for your particular application or use case. One such startup which benefited is the Drive Blocks based in Munich, Germany. They are a team that has evolved from the TUM Autonomous team, which won the Indie Autonomous Challenge in 2021. Let's look at the journey by hearing from the CTO, Alexander Wisniewski.
Hello and welcome. My name is Alexander Wisniewski and I have been the team leader of the TUM Autonomous Motorsport team, a team of about 15 researchers and 40 students of the Technical University of Munich, taking part in an international competition for autonomous racing vehicles called the Indie Autonomous Challenge. Overall, there have been about 37 universities taking part in the competition, with 9 universities making it to the final. The competition was all about letting autonomous race cars drive autonomously around the big oval racetracks in the US, which are the Indianapolis Motor Speedway and the Las Vegas Motor Speedway. Those vehicles are capable of traveling up to speeds of 270 kilometers per hour and do the full autonomous driving tasks, so doing object detection, prediction, planning, and motion control. What has been unique about the challenge is that there was only 8 weeks of preparation time where all of the teams had to share access to the racetrack. So testing time was a really scarce resource, and even a single failure could lead to severe damage because each of those prototypes are about $1 million, and a touch with the wall can be the end of the competition for a team. How we tried to overcome this challenge is that we used simulation as a key development tool. We developed a vehicle dynamics simulation based on MATLAB Simulink and deployed this on a hardware-in-the-loop simulator built by Speedgoat. This allowed us to build not only 1, but up to 8 autonomous vehicles in a fully real-time hardware-in-the-loop simulator. This testing capability enabled us to not only test single vehicle scenarios, but also to actually build racing scenarios with multiple vehicles racing each other and not only being simulated by easy or let's say non-realistic driving behavior. This was complemented by a 3D visualization based on the Unity game engine, which was enhanced by custom developed sensor models for LiDAR, camera, and radar perception. This strategy allowed us to develop new software releases and test them thoroughly within a time frame of 24 hours, which put us in which gave us a crucial advantage compared to other teams. We think that real-time testing was one of the most important factors in our success because we were able to win the October competition and scored 2nd place in the competition in January 21 at the CES in Las Vegas. So what to do with all of this? So we have been spinning off the company which is called Drive Blocks, and it's a startup originating from the TUM Autonomous Motorsport team. The key focus of the company is to develop a modular and scalable software stack for commercial vehicle autonomy. Even though those vehicles will not drive at speeds of about 270 kilometers per hour, real-time testing is going to be a crucial factor as well. And the one thing which we have learned at the racetrack is that an iterative development process is really critical to success. So being in a position which allows you to test your new software and thoroughly validate it before putting on your prototype is going to be a huge advantage in comparison to the competition.
Thank you, Alex, for showing our audience the importance of real-time testing of controls and how it played an important role in getting your work from the student competition to a startup. The examples so far for the different focus areas highlight the effectiveness of the Speedgoat plus MathWorks system in handling real-time prototyping and testing of controls. But then, how do you start off with this workflow? A reference application along with the development kits is a way to easily understand the Speedgoat workflows with real hardware. In the next part of the webinar, I will walk you through the entire process on how you can start off with this kit, which will help you teach your students real-time controls design and testing concepts, and can help researchers get a reference point to start developing their applications. For your reference, these examples are covered in the Speedgoat electric motor control reference, which you can download online for free. The link is provided here. We will first begin with desktop simulation of motor and motor controller based on the plant controller system. The first step includes creating a high-fidelity model of your brushless DC motor. Here, you can see the permanent magnet synchronous motor or the PMSM model. If you look inside the plant model, you can see that the motor is modeled as a SimScape network. The controller over here is modeled as a field-oriented controller. The first step to do would be to perform model-in-the-loop simulation. For accurate analysis of the model, you would like your Simulink model to behave exactly like how the real motor behaves, meaning the model becomes a true digital twin of the real motor. This can be done with feeding external input data to the model and tuning the behavior of it. A quick way to do this would be to use a signal editor block to manually define some custom control inputs. The signal editor block allows you to add new signals and scenarios easily. Here, you can add a blank signal and simply drag and drop points and lines to build the signal. You can then correct the values of each point using the table below. Or you could do a freehand drawing of your signal. Or you could add an expression, which in this case is a sinusoidal signal. For a test, however, we can use the predefined closed loop goes down scenario and run it. This tells the controller to spin the motor to a constant velocity and turn it off again. The speed of the motor depends on parameters such as motor inertia and various friction coefficients. We run this model now and generate some output signals. To achieve our goal of making a plant model accurately mimic the real motor, we can compare the response of a Simulink model to the behavior of the real motor. To do this, we need to get the response from the real motor, which can be done by modifying the existing model and using the I/O interfaces in place of the plant model. The I/O interface is then connected to the real motor. Setting the control inputs to the same goes down scenario, a single click compiles and runs the model on the real-time target machine. To compare signals from different runs and to compare desktop simulation to the real-time application, the Simulation Data Inspector can be used. The pink line in the plot here is the rotor velocity from a real motor experiment, and the blue line is from a desktop simulation model. The response to the coast down scenario is different, indicating that a parameterization of the motor model can be improved. We could manually look into the model, change some parameters, and perform additional runs for comparison. But MATLAB already provides the Simulink design optimization to automatically find an optimal set of inertia and friction parameters so that the response of the motor model mimics the one from the real motor. Let's open the Parameter Estimator app directly from the Simulink toolstrip. It is important to set active configuration to the MIL model. If we click Plot Model Response, we also get the simulation output from the current set of motor parameters. Now, we are ready to start the optimization process. We can observe the progress in the plot. As the parameters are adjusted, the response of the digital twin gets closer and closer to that of the real motor. At the end, we have a new set of optimized parameters which we can fill directly into the model, and a motor model now very accurately replicates the real motor's behavior. We are going to use this fine-tuned plant model again when we talk more about hardware-in-the-loop testing. After designing your controller model in desktop, it is time to create a real prototype of it using real hardware. To design your controller, you would like to create a prototype of it and connect it to your plant. You can use the created model of your controller in Simulink and deploy it onto the Speedgoat test system. This way, the Speedgoat test system itself acts like a prototype of the controller. This is called as rapid control prototyping. The system now looks like this. The prototype of the controller is connected to the real plant under test using the I/O interfaces from the test system. With the case of the reference application, the plant is a real motor. Let us look into how we can use rapid control prototyping to prototype our motor controller in the reference example. The field-oriented controller employs PID control for the velocity control loop. We start with a reasonable estimate for the controller gains, which we have got through testing against our desktop simulation model. We can verify and fine-tune the control parameters against the real motor. You can connect to the target machine either using Simulink Real-Time Explorer or directly connecting a pre-configured target. As shown earlier, by the click of a button, the model is built, deployed, and runs on the target. You can see the motor spinning on the right. You can see the dashboard here and see how useful it is in prototyping your controller. You can see the button to change the speed to any value you want, or alternatively, you can also enter the exact speed. Depending on your application, you might need to update multiple parameters simultaneously to test a desired effect. You can change P and I gains also in real time. The graph below shows the referenced versus measured speed of the motor. When you change the referenced rotor speed, the measured speed also changes automatically. You can see the various parameters of your system in real time, giving you a good idea on how to change multiple parameters in the system. In the end, you can also update all the parameters of a model in real time. The development of a controller is now easily possible to show to your students in real time. This seamless operation is also what researchers in academia need when they develop their control algorithms. One such startup, which came through academic research from Carnegie Mellon University, is Human Motion Technologies, or Humotech in short. Let's hear from the Vice President, Gabriel Forsyth.
Hi, I'm Gabriel, VP of Growth at Humotech, where we're supporting research and development of prostheses, exoskeletons, and other wearable machines. We accelerate discovery of innovative real-world solutions to enhance and augment human mobility through CAPLEX, a testbed for systematic exploration of the mechanics of wearable machines. We support R&D in academia, healthcare, government, and commercial spaces. Now, by way of introduction, I want to show you a short video that was produced by MathWorks. Humotech's mission is to transform the way the world develops and uses exoskeletons, prosthetics, and other wearable machines.
The CAPLEX system is a wearable robotics platform for other innovators to develop upon. It involves physical wearable devices tethered to off-board actuators. It also includes a software component that controls the actuator in real time to regulate the torque applied by the wearable device.
The emulator creates the physical sensation of wearing different devices. So for users, you put on one emulator and try on a host of devices, switching from experiencing one device to the other in between steps without even breaking stride. Being able to compare two devices back to back makes the comparison for the user more precise. Those subtleties might be lost if there's 5 minutes between trying on one device and the next.
Whatever wearable device you have in mind, this sort of serves as a system where you can take that idea and just try it right then and there.
The CAPLEX system came out of work that was done at Carnegie Mellon University.
I mean, as we were starting our company, the MathWorks and Speedgoat tools were just sort of there. I mean, they were right where we needed them when we needed them. The price was right, the functionality was great, the performance was awesome.
I think if we did not have access to the startup program at the beginning, it would have been very hard to really get things going.
So there have been several cases where I've gotten stuck and reached out to MathWorks technical support and gotten some very valuable insights that cleared blockages in my way.
We want to help our customers focus on the stuff that's really interesting to them and really groundbreaking for the field. We hope to create a future where orthotics and prosthetics are developed in an evidence-based, systematic way using tools such as CAPLEX.
I also want to briefly emphasize how great a partner Speedgoat has been for Humotech, not only for supporting Humotech and building this wearable robotics platform, but also being a great tool for our customers. Our customers, like I said, include academic, clinical, commercial spaces where users and operators of the system have wide varieties of focus areas and technical skill levels. So we need the system to be both very accessible and very powerful and deep, and Speedgoat fits right in there. So they've been a great partner. So one of our customers is the VA of Puget Sound in Washington. They applied for a grant to study the feasibility of a test drive strategy for prosthetic foot users, whereby the user or patient could walk in an emulator like the CAPLEX system and have the prosthetic device, the emulated prosthetic device, behave like real, already existing prosthetics. So the hope would be that this would increase satisfaction among prosthetics users and lead to better outcomes, so they could pick the device that was actually best for them. So hopefully this gives you a sense of what is possible with a CAPLEX system and how Speedgoat is helping to enable the future of wearable machines. Please feel free to reach out if you have any other questions or are interested in learning more. Thank you so much.
Thank you, Gabriel, for showing how Humotech helps individuals leverage the best available technology in order to realize their mobility goals. Let's go back to a plant controller model. Let's say that you already have an embedded controller implemented. You would like to test their operation in real-world scenarios. You could connect your controller to the real plant. This would, however, risk damaging the real system. This is where hardware-in-the-loop testing can help. You can create the model of your plant in Simulink and deploy it onto a Speedgoat test system. This way, the Speedgoat test system itself acts like a digital twin of the real plant. The system now looks like this. The digital twin of the plant is connected to the real controller under test using the I/O interfaces from the test systems. This way, you can test your control in real time with real-world scenarios. With the case of the reference application, the controller is a TI microcontroller. Let us look into how we can use hardware-in-the-loop testing to test our motor controller in the reference example. For automated hardware-in-the-loop testing, we can use a test harness to apply different stimuli to the model's root-level inputs. A test harness is an encapsulating Simulink model which allows us to connect multiple test inputs and verification statements to our system under test. A test harness can be quickly created for any model by right-clicking and selecting Test Harness Create for Model. In this case, though, we already have a harness in place which I can quickly switch to using the Perspectives view. You can see that this looks like any other Simulink model, but it includes a reference subsystem with a system under test, and we are using the test sequence block to define the input signals for the different test cases. The test sequence implements closed-loop testing using step transitions. At 1 second, the motor is turned on, followed by a verification step where we check that the measured velocity lies within the tolerance. We repeat this process with the velocity command in the opposite direction and verify again. We can run the test sequence in desktop simulation first, add breakpoints to the sequence for debugging, and then manually deploy the model for real-time execution. But you see, we have ended up with multiple different models and test harnesses already. We can avoid managing them all manually and instead use the Simulink Test Manager for full test automation of our test management, execution, and evaluation for both desktop simulation and real-time tests with hardware-in-the-loop. We can open the Test Manager directly from the Simulink toolstrip and see our pre-built test setup. The first test is named MIL or model in the loop, so this will run entirely in desktop simulation. The second one is rapid control prototyping, a real-time test, which means the model will be executed on a real-time target machine. You don't need to create each test from scratch here. We can easily make a copy of our desktop simulation test and convert it to a real-time test. Like this, you can maintain the configuration such as assessments or parameter overrides. We'll be using hardware in the loop test now, which is a real-time test set to run on a default target machine. At the top, we also define the model and test harness to run. In other sections, we can, for example, override model parameters. We will change the inertia of the disk driven by the motor to see how our controller responds to that. And finally, we have multiple assessments which we will be automatically evaluated to determine if our test was successful. These come in addition to the verify statements in a test sequence block. So, we can just run this test case now by clicking the Run button. Our test is now run for each parameter set automatically, which takes a bit of time, so we'll fast forward it a bit. In the end, we get all of the results nicely structured and can immediately see the tests were passed. For more detailed analysis, plots of the signals and outcomes of the verifications can be visualized. Once we have a complete set of results, we may want to export them for a later analysis or documentation. We can select the test cases we want to generate a report for and click on the Report button. There are multiple fields we can customize and checkboxes to enable which content we want to publish. We are going to create a report in PDF format, including plots of the assessments and simulation outputs. After just a few seconds, we get the complete report for later analysis. You are now ready to have your electric motor control designed, implemented, and tested. With this, let us go back to a real-life example in the form of a master thesis, where the research used hardware-in-the-loop testing and was done in collaboration with Speedgoat using Speedgoat hardware. This master thesis was done at Uppsala University in Sweden on design, simulation, and hill testing of electric scooters propulsion system. The entire modeling was done using Simulink, with the controller modeled as field-oriented control and the plant modeled as inverter and a BLDC motor. To test the embedded application in real time, hardware-in-the-loop testing was done. The setup contained the controller and the test, which is here the C2000 microcontroller, and the digital twin of the inverter and BLDC motor on the Speedgoat hardware with I/O modules, which is running in real time. The results showed the sinusoidal three-phase motor currents with the back EMF in trapezoidal manner. With this, let us look at some of the key takeaways from this webinar. Among various endeavors in the field of academia, use Speedgoat plus MathWorks solution for research, teaching controls design to students, student projects, and to accelerate innovation from academic research to a startup. Benefit from ready-to-use reference application with the electric motor control from Speedgoat to perform model-based design, model-in-the-loop simulation, rapid control prototyping, and hardware-in-the-loop testing. See how other professors, students, and researchers are using Speedgoat test systems with Simulink. Thanks for staying with us until the end of this webinar. For more information, just visit our website, speedgoat.com.
You want to learn more about real-time controls testing? Then find additional content linked here.